I'm also happy to see I have over an hour to talk about BGP because we're very early, right? No, that's too much BGP. Yeah. Okay, so we're going to talk about stuck routes or ghost routes or BGP zombies, as we call them here. We were happy to host Ileana, an intern, a PhD student over the summer, and she did this work, and I am going to tell you more about it now, with beginning with what are BGP zombies. Let's try to understand the problem. Let's imagine that we have 3 autonomous systems here, and they are connected like that. So if the first AS has a prefix, then they create a BGP message. It's called an announcement, and they have the prefix here that they want to send. And they send this message to the next AS, and now the other AS knows about the prefix as well, and it's being passed down to the chain until the entire internet is aware about this prefix now exists over this particular path. And when a prefix is no longer available, or a link is down, or something happens and this is no longer valid, and a BGP update is generated and sent. This is a withdrawal, and it is being sent down the same way the announcement is. However, in some cases, these messages get lost. They're not being processed. And right now, if this happens in this example, we have this prefix, and the first 2 ASs, they say this doesn't exist. Like, I received a withdrawal, it's gone. But the last AS, it still thinks this is a thing. Like, it still has it in the routing table, and it's going to send traffic to the second AS if it ever has anything destined towards that. And if the third AS has customers, because it never received the update, it will never send it to its customers. So everyone under this AS will also be infected by this zombie. So why this is a problem? The first thing, the obvious thing, is that you don't want to have wrong routing tables. Like, your routers have one job, to push packets to the right destination. So if they don't have the correct destination, they're going to make mistakes. The other thing is that if you do a lot of traffic movement, like if you have traffic engineering or you have a DDoS attack, as we've seen, then you may create new paths in BGP, new updates. You withdraw them like after the attack is over, and you still have traffic going over that other path. If you have, for example, DDoS mitigation by a provider, and you have, let's say, 8 hours a month or something like that, if this route is stuck, you're going to get, hundreds of megabits, like a gigabit through the provider still, and they may still, use your quota. So other things is that, you sold some IP addresses to someone else, and they have, 0.1% packet loss, and you cannot troubleshoot it. It's not in the network. It's just that this traffic is being sent to something that doesn't exist. So, of course, the number of prefixes is also growing, and eventually, if these routes are getting stuck forever, like we have routes that were stuck 10 years ago, we're going to have this pile up and create problems. The important thing here is that it's not just your prefixes getting stuck somewhere else. Maybe you have someone else's prefixes stuck on your router or your upstream's router. So both of these are a problem. And something else to mention here is that we talked about what happens when a withdrawal is lost, that you still think it's there and you're sending traffic, but an announcement can also be lost. So, and since there are more announcements, it may even be more likely. So some links, you may have set it up, BGP is working, and one of your prefixes is not going through that link, because that message did not go through. But we have, like, as network operators, we have hundreds of problems, from DDoS attack to quantum attacks to all of that. So is this a big problem? Like, should you care about this? Is it something that you should spend time on? And Ileana is an academic, so she looked at the literature, And the state of the art currently seems to be this paper here, where they try to analyze what is going on. Like, what's the percentage of routes that are getting stuck, which equipment perhaps is most vulnerable, which provider, and so on. And what they do is that they use a RIPE service, the RIS beacons. And this is basically operated in 25 locations by RIPE NCC. Every 4 hours, they advertise a prefix, and then 2 hours later, they withdraw it, and then 2 hours later, they start again. So they create this sort of pattern there, like a beacon. And they have IPv4 and IPv6 prefixes that they are doing. So if we look at a visualization, this is it over time, and in the green arrows, you can see the prefix starts getting announced. In the red, it is being withdrawn. And now you may notice that it's not completely withdrawn, so there is some visibility still. This is the result of the stuck route. So there are some networks where this is getting stuck at, and you may notice that it's not going to 100% or it's going down slower. This is not related to that. It's a different kind of problem. So visibility of these prefixes, because they go up and down a lot, is not the typical prefix that exists. So what the researchers did was they knew the schedule, so an hour and a half after the prefix was withdrawn, they went to the RIPE looking glass, and they said, okay, give me all the routes you have for this prefix, and it should be empty, ideally, but it was not. And they found that this happens hundreds to thousands of times in the periods they studied. Now, we think that there is a typo here, like this 2018 is 2017 there, but it still happens quite a bit. We wanted to ensure that this was done accurately, so we tried to replicate the study to make sure our methodology works, that everything is fine. And since we didn't have a time machine to query the looking glass, we had to replay all of the BGP messages of that day to make sure that we get some correct numbers. And we identified that because we use a different method, maybe better, hopefully better, that the problem is actually a little bit worse than what they found. And it's still something that is happening today. So the issue here is, as I said earlier, that we get these zombies. Like the prefix is still visible by some networks, and it never goes down cleanly to 0%. If everything was perfect, we would be like this, basically. Like no network would see this prefix during its downtime. The problem here is that imagine if it was the other way around. Like if this route was stuck in the first box, then maybe it remained stuck until the peak there. Then it remains stuck during this pulse, let's say. So we looked at an option that RIPE has available. They use some aggregator addresses in BGP. So they publish the number of seconds since the beginning of the month, so we can know when an advertisement was made. And we use that to try to correct for that, like to make sure that this route was stuck 1 hour ago and not 1 day ago. And the numbers did not change too much. So we are confident that this is the number of zombie outbreaks that happened during this period, each of the 3 periods. So the interesting thing is that around 19% of the RIS peers were not affected by a particular prefix. The remaining amount of RIS peers, they're like over 1,000, they actually had at least one route that was stuck there. And on average, it's around like 0.5% and 1.6%, depending on the protocol, of the probability of a prefix being stuck in a data like in an AES that provides a feed to RIPE RIS. And this is not great. Like 1% of the updates getting stuck somewhere is not fun. The worst thing is that over 90 and 95%, depending on the protocol of the time, this was not the best path. So the path that remained there was a suboptimal path you probably don't want your traffic to be taking. And this is something that increases the impact that these hijacks, these stuck routes may have. But we looked at this methodology and we said, okay, like, can we improve that? What else can we do to try to understand and quantify this problem better, to see if it's relevant for the community? And if you look at this again, you can see that there is a gap of 2 hours. So the most we can study is what happens in this 2-hour period. We cannot study what happens a day later or a month later. And for this, we created the BGP clock, which is an interesting idea to try to get around that. We have a prefix here. We're using IPv6. I tried to expense an IPv4/8 on my corporate credit card, but somehow it was rejected. I couldn't get the charge through, so we're using IPv6 for that. We advertise a prefix that has the hours and the minutes in there. So if it's 10 a.m., we have the prefix like 1000/48. And this allows us to see 24 hours into, until this repeats again on the next day. And then we changed it a little bit. We added the date there to make it repeat every 2 weeks instead of every 24 hours. And then because this is important in the modern internet, you need to use RPKI. I signed the routes with a ROA, and I had the source AS set to the correct one. And so we created this BGP clock service. The similar methodology has been used by Ben from BGP Tools as well. And there are a few advantages. The first one is that we can look more into what happens, like we have a larger duration. Then we have more prefixes. We do that 4 times an hour instead of 4 times a day. So it's like if this is something that happens 1% of the time, we roll the dice way more often than what the RIPE RIS beacons do. And I have a personal AS, 210, 312 there. I have over 1,700 direct BGP connections through internet exchanges and other means. And I advertise this from my personal AS. So this was basically sent to a large number of networks directly, didn't go through transit providers too much. And some interesting findings. We have this particular prefix. It was stuck in 6 ASs, and this is the common path. So we think that it was stuck somewhere in FreePro, which is an AS in France. They have over 200 ASs in their cone, and although we don't have data from them, we assume that if 6 of them that were infected, probably everyone else had this route stuck into them as well. And the visualization here is going to make this easier to see. You can see on the far right is the origin, which is my AS, and as we're moving towards it, we can see in the red square the AS where we think the problem is happening. And it looks kind of like a sideways palm tree where you have a very long trunk, and then you have all the leaves at the other side. And this allows us to identify where a route is getting stuck. We're not blaming this particular network. It's not that they did something wrong. Maybe their upstream did not send them the update. But for whatever reason, only this network and its downstreams was infected, in quotes. So if it happened before that, if it happened in open transit, for example, you would see all of their downstreams infected as well. And if it happened under free SAS, it's extremely unlikely for all of their customers to have been infected at the exact same time. like all of their equipment malfunctioned at the exact same time. This is unlikely. So this is how we have some kind of attribution on where this may have happened. Another interesting network was in Core Backbone in Germany. This is a larger network. They have over 2,000 AESs in their cone. And this has been found many times by Ben of BGP Tools as well, to have routes stuck to them. I personally believe it is the specific equipment they are using, but they had quite a bit of, like they had many prefixes that we create stuck in their routers. And again, we think that all 2,000 of their customers received this route. It wasn't just them, it's just that we only have 24 of them giving us their BGP data so we can know like what happened. And finally, we found another German network with over 200 AESs. We had like hundreds of prefixes that were stuck in ISPs, but these are some of the largest ones. Like they had the most customers that they in turn caused an infection towards. And we ran this for a little bit less than a month this summer. And because we wanted to stop it, like this created too many BGP updates on the internet, it may not have been super useful to keep it going unless we were looking at the data. I stopped the advertisements. I deleted the ROA from the RIPE portal, and then kept doing other things. And then I received an email, and this email is from RIPE, and it says, hey, you have RPKI invalid messages. And they sent you basically a message. If any of your prefixes are not covered by your issued ROAS, they will notify you and they'll tell you, hey, you may want to issue a new ROA to fix this if this is intentional. If this is a hijack, take care of it. And it's been 3.5 months. I still receive this email. So they send it periodically. They have a cron job or something. They check if the prefix exists, if it's invalid, and they notify you about it. So we have made progress, however. Like there was one prefix. It has been recently removed from RIPE RIS. But two other tools is BGP Tools that I mentioned. There are still 2 prefixes stuck there, and Hurricane Electric's BGP Toolkit that has still 2 different prefixes that are stuck in their feeds. And this is an interesting method, actually. If you want to start the RPKI validation adoption, and those pesky IXPs and tier 1s, they drop your invalid routes, what you can do is create a valid route and then propagate it, get it stuck somewhere, and then make it invalid and see if it's still in the routing table or not. Because if it's invalid, it should have been removed. So that's a bonus tip on how to bypass ROV. Did we learn anything from that? Well, hopefully, yes. So the first thing is, this is the probability of something getting stuck for a particular incident. So this is over time. You can see the amount of networks that have been that fell for this stuck route. And the first thing is that there are 2 lines there. Let me explain why we should look at this one, the red one. We found 2 ASs, 3 connections, where like 10% of the updates and withdrawals were getting stuck there. So this is a very, very high rate of routes getting stuck that we had to exclude because it made everything noisy. Like everything was getting stuck in them, basically. So if we ignore these sections, we end up with this red line here. And you can see that after some time, it's going down. So you still have some people where this route remained. Like 2 hours later, most of them are gone, and it keeps going down. But at some point, it started going up again. So the number of stuck routes went up without us doing anything. We didn't touch this prefix, and more people were getting infected by this BGP zombie. So we decided to have a deeper look into that, and it turns out that we saw prefixes being withdrawn around 10 minutes earlier, and then someone generated an announcement. It was not us, like one of the networks out there created a BGP message and basically sent it to its downstreams. And after investigation, we think that this is Telstra Global, which is an Australian company. They have over 5,000 ASs in their cone. So maybe they changed the filter, a link went down and up again, but something made them generate an announcement, and then they sent it to all of their customers. And if they send it to their customers and they prefer it, this new route is being generated, and then maybe they send it to their downstream customers. So what we learned is that reinfections can happen. Like some of these networks in the previous slide, they actually managed to remove that route from the routing table and everything was happy, but then they added it again because Telstra told them to. And again, I don't want to blame a specific network. We still don't know exactly what is causing it. We have some idea, like some specific routers and software versions that are doing this more often than others. We have some implementations where this is not happening at all, but this is something that we are still studying. For example, we still want to do the IPv4 case and try with not a /8, but something smaller, something reasonably smaller, try to recreate this and see what happens in that world. And we plan to reach out to network operators and inform them about that and see what we can do to help them get rid of this problem. There is one solution that will hopefully make it go away, and it is a new draft that's very close to being a standard in the IETF. It is send hold timer expired. So there is the hold timer in BGP, a traditional metric, like if you don't hear back in a few seconds, then reset the session. The send is if you try to send a message for a few seconds and it doesn't get through, then reset the connection. And we think that if the entire internet updates their software after every vendor adds it, so, many years, we think that this is going to solve the problem of stuck routes. So what I can ask you right now to do is to talk to your vendors and request this feature to be added. It's going to be a standard soon, but I don't think it's going to change. It's in editorial review now, if I remember correctly. So just contact your vendors and ask them to add the send hold timer expired into the software. Then at some point update to the software that includes this, and then it will hopefully be enabled and protect you from creating zombies. It will not protect you from consuming them, but hopefully it's a team effort. Eventually, one day we'll get there. That's all I had for you. Thank you very much.